this series of videos I'm attempting to repair and restore a PDP11-34 vintage computer. So far in this series I've been working my way through various faults, and although this machine initially ran, it won't boot now, and it looks like what happened that finally stopped this running was I was trying to boot from floppy disk, and looking at the various faults it's got, it looks like the floppy disk interface card has done some damage to the CPU. Now, the way this CPU is arranged, these two front cards are the CPU, but basically all their in-out signals come down to the Unibus on slots A and B. So it's kind of like a self-contained CPU unit. You can take this out and use the console to test the other cards, which is what I've been doing. Now, it looks like part of the fault for stopping this booting is in the bus grant and interrupt system. It's kind of locked itself into a state where it's not going through a full processor cycle. Now, I will be posting a separate series of videos that goes into a lot of detail as to how this CPU works. It is fascinating. It works like any other CPU really, but the architecture of this is really quite interesting, so I will be posting a separate series of videos that details each of the separate parts of this and goes into a lot of depth as to exactly how it works. But in this series I want to just try and stay focused on the fault repairs. I skipped through the early fault repairs. I didn't really show any of what I was doing, but I've been asked to show more detail as to how I go about fault finding. So although I'm not showing too much of it, it's obviously quite a long and fairly tedious process if it's not something you're particularly interested in. But if you want to get one of these working, you do have to go through a fairly logical process. It's not as hard to work on as it appears, although it is very useful to have spare cards, and more of that hopefully in future videos. But at the moment I only have these cards, so I'm working with what I've got. At the moment I'm going through and testing the in-out signals coming from the CPU. I believe the memory card in this machine is also faulty, and that's sort of contributing to the reason it won't boot up. So what I'm going to do in this video is very briefly show how the console can be used to do various testing, and how the logic analyzer can also help in analysing what's going on. Now, when it comes to looking at a PDP machine, or really any other machine with this type of architecture, you have to remember that the CPU is fairly autonomous in its internal workings, but it will obviously be attempting to get an output data onto the Unibus, and some of those signals can interfere with the running of the CPU. So if there are faults in other cards, it can halt the CPU, and I think that's what's happening with the memory card. It's kind of contributing towards the faults that the CPU has. So to hook up the logic analyzer, I've been looking at various different elements within the CPU. I found a few ICs that are faulty and replaced those. I've replaced the Unibus driver that I showed in the previous video. It did change the behaviour. It's now going slightly further, but it's still not booting, still crashing partway through trying to process an instruction. There are various techniques you can use for this. The main thing I found when working on these is try not to look at it as an entire system, at least not until it runs to a certain extent, and this doesn't. So I look at it in blocks, and I try to test each of those in a logical way. So what we'll look at here is how to use the console to do some basic testing on the CPU, and also in conjunction with that I'll hook up the logic analyzer and we can see what's happening on the Unibus. So to connect the logic analyzer, I've got one of these cards. This is what was one of these, so you're familiar with these. These are riser cards. I sell these on my website, but rather than put a socket on the end, I've just fitted some pins that I can use to hook up the logic analyzer. So it takes 4 pods to monitor all the lines of the Unibus. I've got every single line hooked up, and we'll have a quick look at the logic analyzer in a few minutes. So we'll have a look at the logic analyzer. I'll get this plugged in, and then I'll be putting the 8265 card back in risers so I can work on it more completely, more easily. That does get in the way of the logic analyzer a bit, so it will kind of limit how much I can show you, but I'll just go through some basic testing. So looking at the screen on the logic analyzer, I would say here I don't normally use the Agilent 1670G for working on a PDP machine. I would normally use my 16702B logic analyzer. The main reason is it's got a much bigger screen and I can get far more traces on it at the same time. Quite often you want quite a few traces to examine when you're looking at the PDP machines. You can have just as many on this machine, but it's a much smaller screen, so it's a lot harder to work with. But I can't get that onto the shot with the camera, so I'm showing this logic analyzer, but if you do have one with a bigger screen, it does make it a lot easier. But for the sake of the videos, I'll just use this logic analyzer. So you can see I've got the 18-bit address bus set up, I've got the data bus set, and then I've got all the control lines for the PDP Unibus, and the only ones I've duplicated here, although I've got the BR 4, 5, 6 and 7 as separate bits, I've also included them as a bus. It just makes it a lot easier to view on the screen. In terms of the configuration of the analyzer, I've got it set to state mode and I'm using the CPU clock. That's not the clock on the console board, it's the kind of feedback clock that's used with the delay line on the main CPU board. And the reason I'm using that is because everything is keyed to that and it makes all the data you capture far clearer. And trigger wise, at the moment I'm just looking at a couple of key addresses. So we'll now go back and look at the PDP. I'm just going to put the 8265 board in risers so we can see the entire board, and then we'll try capturing some data. So we'll start by using the console to do some very basic testing of the CPU. Sorry, I've got the fan running again. I need that going to stop the boards overheating. But what we'll do here is, as I say, use the console, and we'll just see if the CPU is functional at all. So there is quite a lot of testing you can do with the console, and I'm talking here about the programmer's console, the one that's plugged into the actual machine, not the console emulator. You need the CPU to run for that to work, but you can use the machine console to do some testing. As I say, I will at some point be posting a series of videos on the inner workings of this. It is quite interesting, but for the sake of this video and the simple testing I'm showing here, the only thing you really need to be aware of is that as with any CPU, it contains a number of working registers, and those registers are used to control the operation of the CPU and also to store data of different types. Some of it is kind of just temporary data, numbers, data that's been worked on. Other registers, although they're part of what's termed the scratch pad area of the memory, and this is not the RAM, this is memory on the actual CPU card. Although it's termed scratch pad, some of the registers are used for very specific tasks, such as stack pointer, program counter, that sort of thing. The ALU works with special registers that are connected to its input and output to allow the CPU to carry out certain tasks. And the PDP CPU is no different. As well as the scratch pad registers, it has some special registers that are connected to the input and output of the ALU. And all of these registers you can access, as long as the processor is halted, you can access them using the console. And that means that if you want to, you can actually load an instruction into the CPU card. It won't be running, but you can load the value that would be loaded if the CPU had obtained the instruction from a ROM or RAM. You can then start it running or try and single step it. When I say single step, I'm talking here about processor clock stepping, not instruction single stepping that the button on the console does. There is a connector for servicing or for diagnostics on the board, and it enables you to do two things. One is to disable the main CPU clock, and the other is to feed in an external clock. It's normally fed in from the console controller to allow you to do diagnostics, but if you want to, you can feed it with single pulses, and that will cause the processor, because it is statically clocked, it will cause the processor to increment through the microcode trying to execute the instruction that you've loaded. And what you can do at every single clock cycle, you just do a single clock cycle, and the processor should move on to the next phase of the microcode cycle, and you can examine all the various parts to see what it's doing. I will be doing that in a different video, as a different video series. As I said, I'll post a video series on how this works, and we'll go through how to do that in that series. In this series I want to try and stay focused on this repair. So what we can do is turn on the PDP. We'll put it into the mode we need it to access, effectively manually access the CPU. And what we can do now is start looking at various addresses. So for example, I have a 9312 plugged into this with the DY boot ROM, and so if we look at the boot address for that, and what we're trying to do here is to determine whether the Unibus is working. There's no point reading the register that's internal to the console. We need to read another card that's plugged into a different part of the Unibus. But what we can do is access that the start point, the start address of the boot ROM. And if we enter that as the target address, so it's 773,000, that's because I've got the ROM plugged into the first slot of the 9312. Maybe a different address if you've got a different ROM plugged into a different socket on that card. We'll load this address. What we can now do is examine the address, and if we get the correct value, we'll know several things. Firstly, that the Unibus itself seems to be operational, and secondly, in terms of the address, and secondly, that the control and data lines, at least to read an address, are functional. So if we press exam, I'm getting a value of 42131. It's octal, of course, and that is the correct value for that boot ROM. Not only that, but you can now step through and look at the next addresses, and you'll either recognise that if you've been through this before, or if you look at the essentially the decompiled version of that boot ROM, you'll see that this actually matches. So we already know now that the Unibus itself is working to a certain extent, that is, all the connections seem to be intact. Doesn't necessarily tell us the connections to the CPU are intact, but at least we know that fundamentally the Unibus is working. What we can now do is start looking at the registers within the CPU cards themselves. So if we start with the general purpose registers, there are really 16 registers in the scratch pad area of the CPU itself, and we've also got a program status word, which is kind of a separate register. It comprises of a few discrete ICs, but essentially it's a 12-bit register, and we'll start with that. We'll read that first. It's mapped to address 777776, and if we load that as the address and we examine it, we'll get the status word, and we're getting an odd value. That's the negative result flag, so it should be 0, but it's not. So it's going to try and restart this and see if that is still there. That's gone away. I think that might have been something that happened during the boot up. It probably didn't boot up very cleanly. There are other faults on these cards, but we're now looking at the contents of the status word. We can also look at the contents of other RAM addresses. So that's the address of the status word within the CPU, and the fact we can read it means that at least we think we can read it. We don't know if the data we're seeing is actually correct. You can force the CPU to do certain things and see if that's reflected in the status word. But now we'll look at the general purpose registers, R0 through R17. Again, that's octal. So if we start with the first one, and these are mapped to address 777700, we'll load that address, examine, and we can now just keep pressing exam and we'll be able to step through the values that are stored in the CPU registers. Now it is of course halted, so these are the values that were there when we booted or tried to boot the CPU up and it failed and crashed. But if we keep going, you notice at some point the bus error light will come on, and that's because we've kind of gone off the end of the mapped registers and we're trying to read an address that doesn't contain anything, so it's timed out and there's a timeout timer on the CPU that causes this light to come on. So now we know several other things. We seem to be able to decode and access the scratch pad registers successfully, and also the bus error timer seems to be working. Look at the address, we can see we are at the address we would expect to be. The last valid address is 777717, again octal, and we're at 777720, which is the address after that, and that's what caused the bus error light to come on. There is no register mapped to that address. But we can go further than this. If we reload the first address, we can actually store values there. So if we start off with a 1 and we deposit 2. Okay, so I've deposited some values, I think, in the scratch pad registers. If we display the address, we can see we're almost at the last one. And if I now reload the start address, or the address of the first of those registers, and we examine, you can see that the values I try to write to those registers are actually correct. So that tells us more. Not only is the decoder working, because we're getting the correct addresses at the different registers, so it is definitely selecting the registers. We can also read and write these registers, and we can do the same thing with the other registers within the CPU, and we can force it to do various things. We can load instructions into those registers with the processor halted, and then, as I said, we can apply clock pulses to the it's still the same circuit that is used to generate the main CPU clock. It's a bit of an odd circuit, and we'll look at that in more detail in another video, but we can kind of force feed its instruction clock cycles and then examine the CPU as a whole at each step, and that will give us a very good indication as to why it's not working. And I will do that in a future video, but not in this one. It'll be quite a long series of videos. It's quite a complex thing to try and explain. The last thing I want to do in this video is we'll do the same thing we've just done, but looking at the logic analyzer. And this will tell us what's happening on the Unibus, so we'll know what the signals are on there and make absolutely certain that it all ties up and does exactly what it's supposed to be doing. So I'll move the camera, we'll have a look at the logic analyzer and see how we can go about examining the Unibus while the CPU is trying to do its thing. So looking at the logic analyzer, I've got it set up to trigger on certain events, and in this case I'm looking for address 3F600 in hex. Now that's address 773000 in octal, and if you recall, that's the boot address for our DY boot ROM. And also the first value we expect to see there is 042131 octal, and in hex that's 4459. Incidentally, I could change this to display, in fact I will change this to Sharp Tool so it makes it clearer as to exactly what I'm doing here. So octal is good for software, hex is good for hardware. So we're now looking for a trigger on address 773000. Remember, this is on the Unibus itself, and we're looking also at the same time for a value of 042131, which is the data value we expect to find at this address. If we go to waveform and we'll arm the analyzer, it's now waiting for input. So what I'll do now is I'm going to use the console to try to examine that address, so 773000, load the address. I'm now going to press the examine key, and as you can see, not only have we successfully hit that address, we've also got the correct data. I would say at this point, if we go back to look at the format, I've got address and data inverted. They are of course active low signals, but to make it easier to, I don't keep converting between high and low values, I've got the inputs inverted to the analyzer, and it will then give me the values that the CPU itself is working with, although the values on the Unibus itself are of course inverted. So you can see how this can be used to examine the Unibus. You can start looking at the control signals, you can look at the bus grant, interrupt signals, all the handshaking, everything else that's going on the Unibus, and you can fairly quickly narrow down particular faults. As I say, unfortunately this machine's got quite a few faults, and I'm hoping to get a spare card or two to assist in the fault finding on this. Incidentally, big shout out and thanks to everyone that's reached out to help with this project. It is very gratifying that so many people are willing to help, and there's a lot of interest in these machines still. As you can see, there's quite a lot you can do in terms of fault finding on these particular processors and these machines. You can use the logic analyzer, you can use the console itself. Once you get the kind of the hang as to how to best go about fault finding on these, they're not too difficult to fault find on. The main issue I'm having at the moment is I don't have any information on the memory card that's plugged in, and I don't have any information on the contents of the PROMs, but I'm hoping that's something that is going to be resolved in the near future. So as you can see, there's a lot of work involved in getting one of these working. I generally skip through all the legwork when doing this sort of thing, but I've been asked to show a bit more of this, so if you're not interested in this, then by all means skip through the videos. If you want to see even more detail, then leave a comment. As I say, I will be posting a separate series of videos on how this particular CPU operates. We'll go through every single block in detail in separate videos, but as I say, in this particular series I want to keep focused on the repair.